browser, he's next door. We're here to talk today about something that eats my favorite fish that I usually talk about, but a really neat opportunity came up to work with Jess Best and others at Hudson River Fisheries Unit and started to think about using a really long-term data set to try to get our heads around current status and changes in striped bass spawning individuals in terms of a long-term index. So this is going on in conjunction with the ongoing 2026 ASMFC benchmark stock assessment for the species, and I'll get right into that as we go. So for those of you who aren't familiar, striped bass is a diadromous fish, and they all look just like that, I swear. This is the kind of thing that should get you excited about migratory fish if you're not already. So there's a striper with Jess out in the survey we'll be talking about today. Hugely economically and ecologically important, economically sustaining recreational and commercial fisheries that are valued at outlandish amounts compared to many of the species that we work with inland. And because of that, they're intensively managed throughout the coast with a few main spawning populations. We've got indices for the Chesapeake Bay spawning deem as well as the Delaware Bay spawning deem. And a priority coming out of the most recent stock assessment updates was to establish some kind of index for adult striped bass in the Hudson River, the sort of remaining unicorn and the coastwide metapopulations here. I'm taking a lot of artistic license here, Jess. I apologize for coming off at any point. But a herring biologist talk about stripers anyway. And so that's really, we're off to the races thinking about that. We're in the Hudson River here. We're in the watershed, I guess, today. This is a look at the study area. You'll notice in the inset, you may or may not be able to see, there's actually just one more dot way down here, but it just made the rest of the map look bad. I want you to be aware that it's there, but I'm zoomed in on what are the sort of long-term historic as well as some newer sampling sites in the Hudson River. So the black dot all the way at the top is Troy Dam, Federal Dam, whichever you like better. And we got some major cities down along the way on the Hudson that were used for landmarks. We talk about sampling regions very generically. They vary in geographic range and really have just been established as names for sort of sampling these fishes over time. This survey has been going on since 1985. It's a haul seine survey, which is wicked fun if you've not gone out and dragged seines all the time. It targets adults, presumptive spawning component of the population there, and we're going to roughly split it into 4 regions. We'll talk about Kingston and Catskill. These are long-term sites that have been sampled since '85, in addition to Coxsackie and Albany, which have come online. Well, I'll say more recently. There's still like 20-year-old sites in the data set, though, right? So some of these data are older than many of the folks in the room, which is kind of cool. Not me, unfortunately. So I want to give you a quick breakdown and walk through. I preach about this a lot in class, and some of you maybe are sick of hearing it. We've got a lot of data going into this. There are 300, 500, and 1,000 foot haul seines, not 100 foot haul seines. They've been used differentially over the years. The top one is the 1,000 foot haul seine. You've got the same length on the y-axis there, and year of study on the x-axis. You can see that the 1,000 footer was only used kind of early on, once or twice later on in the survey. The 500 foot, most consistent, kind of sampled throughout. You also notice that the colors are a little more on the warmer side than the cooler side, unless I've gone and been incredibly non-inclusive by using a non-colorblind friendly color scale. I'll change it, I promise. So we looked at standardization, potential, like, standardized catch based on seine length and seine area. If you calculate the area of a circle, and it just became like a lot of silly math to get at a number that we could probably get out of the 500 foot haul seine in and of itself. So we're going to drop the rest of them for now and take a look at the 500 foot haul seine data. Note these scales are changing, so the colors aren't always going to be the same. But here you got a similar setup. You got year on the x-axis, and then you got river mile on the y-axis to give you an idea of the geographic spread. You can see that the different sites are, again, variable in their geography. Some of this related to access and the like. If you've worked on the Hudson River or the estuary much, a lot of times it's easier to drive around than to haul all the way up the river for the day, especially depending on navigational traffic. So here the color is again catch. It's capped out at 30. Some of these catches are way bigger than 30. Some like 400 something is the biggest one. You go ahead and keep that in mind if you're into statistics. Some of those sites are long-term. Catskill and Kingston I'm call long-term here, and Coxsackie and Albany again more recent. So we're interested in what's going on with that, how that might affect estimates of relative abundance of the population if we're thinking about an index of population size that we're trying to get at overall here. Sample size, number of halls is the size of the circles there, chopped up into bins, so you can see how that's kind of been apportioned differentially over time and space as well. And these are some important things for us to be thinking about because the survey was not originally designed as a population index survey. It was designed to catch striped bass so they could be tagged for other population monitoring purposes, right? And these kinds of data sets languish out there in the world just wanting to be used, but they weren't, stratified, random sampling designed, and along comes some nerd who wants to put a spatial and temporal backend on a Bayesian hierarchical model and say, maybe we can do this. So here's what we're dealing with. I just knew everybody in here who's got stats experience because you winced visibly. This is your typical count data set in ecology, really. It's highly skewed. Many zeros in the data set. About 35% of the Hall-Sains resulting are empty. About another 36% of those empty, 35% ones. And then you've got these just monumental catches, 422 individuals. So we're dealing with a lot going on here. And so if you're into modeling, you really start to beat this stuff up and you go through diagnostics for weeks and weeks and weeks on end, and you get really frustrated. You say, I'm just going to do whatever I want to do. You don't really say that. And so we trim a lot of this out by narrowing down the data set, thinking about those kinds of things. We go through a process of model critique, criticism, if you like. Look at a lot of different probability distributions. I'm just showing a really common stock assessment approach here. It's called a delta model or a delta mean. If you've got it through a stock assessment, you've gone through a 3-hour conversation about that and maybe still don't understand what it is. It's statistically a hurdle model. You account for different processes and zeros versus ones or counts. So this has been widely popularized in stock assessment in recent years. Really powerful tools that we have at our disposal, and for that reason has been applied to a number of stocks in recent years. This is showing a delta gamma model for folks who are really in the know, and that's because the data are so skewed they don't conform to even a log normal distribution. We played around with Poisson and negative binomial. They really kind of start to fall apart. We get reasonable approximations to average catch here annually. It's not horrible, but the uncertainty is in this situation, I'd say almost kind of so wide that it's uninformative. So we got a really neat squiggly line, and that's about it, right? And I'm a big fan of incorporating and integrating uncertainty into the estimates that we make, but that's just kind of a little gross even for me, let's face it. So what are you going to do? We started poking around and thinking about mixture models, and really the mixture part was secondary. What we're really thinking about is actually using spatially and temporally explicit models of counts, right? So this is just a state space formulation of it. If you're into Bayesian, you can read all this. If you're not, you can pretty much tune out now. But basically what we're going to do is we're going to take a classical and mixture model in this case. We're going to put a spatial backend on that. So big gross kernel smoothing parameters that allow observations that are close in space to be more similar to one another than those that are far apart. And at the same time, we're going to allow these things to vary over time so that observations in time are allowed to be more similar than one another, than observations far apart. And I say allowed because they don't necessarily have to be. We're going to leave that up to the model to kind of estimate for us. And then, of course, the really fun part about this for a modeling geek is integrating observation and error into this process, accounting for imperfect observation, imperfect detection, whether not. It's really easy to see a striped bass in and out, but you might not detect them if they're there, say if water conditions are really wild or not. And we'll come back to that idea here in a little bit. So the really cool thing about this is it allows us to load explanatory variables or covariates onto the back end of each of those kind of sub-processes, so we can look at things that affect our detection ability, the ability to find fish, given that they're there, and we can look at things that affect their actual abundance or their occupancy, whichever you like. You can tell I came at this one from an occupancy background. There's a really powerful set of tools out there that are wrapped up in a package, our package called VAST, I think James Thorson. It's amazing, like it's taking over the world. I could not, for the life of me, figure out how to deal with it with less than a 2-kilometer square grid, because it's built for marine applications. So this is basically the same thing if you're in the know about VAST models. It was faster for me to hand code it than to figure out the smoothing grid for a little tiny area is all. I'm going to jump right into results here and start with detection probability, partly to get it out of the way, but partly to impress upon you the importance that we've got interannual variability going on in detection. This is really more emergent due to the environmental covariates, the sampling covariates that we're considering. So this is what it looks like across time. You can see some years we have a much higher probability of detecting fish, others not so much. But this is not mechanistically in the statistical model, so to speak. What is our effects of covariates, such as the wave height? This is categorical. It's kind of gross, just raw R. Plot of the coefficients over here on your right. But you see you got, I should say, calm is in the intercept. That's a whole like 2-week math lecture. We can talk about it afterwards. But calm conditions are down here in the intercept estimate, along with ebb tides and good sample performance, okay? And so these are just adjustments to those. And we'll come back to these because this is hard for a lot of folks to kind of wrap their heads around, so we'll look at them directly as well. So here is just a box plot. These are posterior estimates of detection probability for different wave conditions. So you've got calm on the left, going all the way up to white caps on the right. This is really interesting, you know, as you might anticipate, you detect fish better in calm conditions than you do in like moderately choppy conditions. Swells maybe just didn't get written down a lot or got categorized somewhere else. There's uncertainty here, and we'll work through, you know, cleaning that up in the meantime. But then we've got really high detection probability going on in the white cap situation. My presumption is that those are rough conditions for people and fish. The fish are in a spot, and it's the only spot you can get to. Well, you're going to be darn good at catching them over there. So it's kind of counterintuitive, but again, these are not mechanistic relationships, they're correlative in nature, right? This one's a little more intuitive. Hey, when the net set is good and you think it's representative of catch, it turns out it pretty much is. We're detecting fish with a higher probability than when there are some problems with the net set. Likewise, tide, this one, ebb and flood really kind of seem to be the vast majority of the observations. That's probably intentional based on the ability to get out there in the river. But then you see you have slightly lower detection probabilities in slack tides, whether high or low. And maybe that's related to fish behavior as well. And then finally, we're getting good stuff to meet the abundant annual trends in relative abundance. I'm going to emphasize relative abundance. These aren't population estimates, right? These are the number of the fish that we think were kind of in the area when we went and set the net. And by we, I mean Jess and crew. And so we've got x-axis year here again. Think of this as an index of relative abundance on the y-axis. First thing that jumped out at me, these are a short number of runs. You hit it with a lot higher number of runs, and those intervals tighten up a lot. The uncertainty is better estimated, thank you. Uncertainty is better estimated here, there's a little control over it. We got some peaks going on here. These, again, kind of line up intuitively with what you see in the raw data. This one really creeps me out because it's out there in the middle, and it jumps way up. That's the year where there was a net with 300 fish, there was a net with 420 fish. These are all of our max observations in the time series. So we did check that. It does seem to make some sense. Come back to the link function for that. This is really difficult to see. It's going to get worse over the next 40 years. We'll have to come out with some kind of really cool visualization that doesn't work in a latex power PDF slide. But you can kind of see the warmer colors correspond with those bumps. I wanted to show people how that spatial back end looks. You have these sort of really high abundance estimates down in the Kingston area, and it looks like that's where a lot of those big patches are coming from as well. You can see the changes in the sampling programs spatially over time. We've not tried to backcast to unsampled areas. It's something we could do, and I should mention that I'm not showing the results from any of the long-term stuff right now. because all of those relationships are virtually identical. All the patterns in estimated relative abundance are basically the same, which is neat if you're trying to maximize the utility of your data set that you're out there collecting for other purposes as well. Covariate effects on abundance, just have it simple here. Looking at temperature, we know temperature is important for striped bass spawning migration timings. It's important for like basically every fish population spawning timings for what it's worth. So we're just going and looking at temperature and a potential nonlinear effect there. Played around with salinity. There's not much resolution in the actual salinity levels, so we dropped that for now. And you see this really neat, I love these kinds of cool nonlinear relationships in life. It's all I ever want to model. But you see that you have some increased local abundance starting around 12 degrees C. That peaks out sometime in midsummer and drops off by like 22 or 23 degrees C, which, thank Pete, lines up with literature, because I was really nervous about that getting ready for this talk. So really cool stuff. We're at the point where I think we're increasing our confidence in these data for index. I'm not 100% kind of like settled into where I want to live in terms of the actual form of the response. What I showed you was a really simple kind of Poisson blink function, which is a cardinal sin of modeling counts. Because of the way the likelihood is chopped up, it seems like it's been really manageable though. The variances are estimated really well. We're going to swing back, look at potential use for negative binomial error structure. Of course, it's going to fall apart. It's going to have issues with finality and parameter identifiability, because it always does. And we're going to look at that gamma model as well, because that really now basically aligns the Bayesian version of a vast model that you can access in the R package there. We've got to run through and do some more GOF tests and model validation. And then the stock assessment subcommittee chair would really like us to look into whether or not we can use integrate age structure. And we're seeing some loose proportional relationships between the adult index that we're estimating and egg and juvenile indices, but really want to kind of tighten that up because that's another big term of reference for the stock assessment. So making moves, baby steps, getting there kind of little by little, but really happy where this is going so far. And then finally, a whole bunch of people out there to thank. Funding and logistics, Cornell, DEC, always great about bringing that to bear. Of course, the data sets, SUNY Oneonta, I'm not using the college logo that they want us to use because it's not round and all the other ones are round. Don't tell anybody, Flo. SUNY Oneonta BFS, huge supporters, time, financial, travel, all that kind of stuff. Of course, the SMFC, Mark Conroy, the SAS chair, Katie Drew, my favorite person on the entire planet, and Wes for juvenile data as well. And with that, I might have run us into the business meeting, but I'm not sure.
Okay. We have time for one question, and then the business meeting for the chapter will take place in this room. So, any
I don't even get to leave?
No, you're a lifer now.
That's true.
Any questions?
Yeah, Chip.
In Chesapeake Bay, mycobacteria is a real problem for stripers. Do you see that in the Hudson? And if it did, would it knock the numbers up or would it knock the numbers down because they're easy to get?
These numbers are indifferent to it because they don't include any information about it.
Okay.
But somebody behind you might know more about that question.
Well played.
Thank you, Dan.
I was waiting to stop.